Hi guys, I wanted to make a video explaining a few things about LEDs, their voltage ratings, and a few basic circuits on how to use them. So, starting off, I have a red LED here, and according to my spec sheet here, it says the red ones will drop 1.9 to 2 volts. And right now I have it hooked up directly to my power supply. As you can see, negative directly to the LED, and positive directly to the LED. Now you do want to be careful when you do something like this because it's very easy to blow up the LED if you run their voltage a little bit too high. So let's start cranking it up. There's 1.8 volts, and there's 2 volts, which is what it's rated for. I can see right around 2 volts. Let's get back on the screen. We're drawing right around, you can see it going up to 10 milliamps. Let me give it a little bit more. There we go. So right around 2 volts, we're getting 10 milliamps out of it. 10 milliamps is a very common current that you want to run LEDs at. That's quite bright, as you can see. Now LEDs will run anywhere between 1 milliamp to 20 milliamps typically. Some high-powered ones will go up higher. It all depends on how bright you actually want them to be and what their rating is. I think the rating for these is a maximum of 50 milliamps. So I wouldn't exceed that with these types of LEDs, unless the specification says otherwise. So let's see real quick what happens when you apply a higher voltage to an LED which is rated for less. So there's 2.1 volts, we're already up to 20 milliamps. 2.2 volts, we're up to 40 milliamps. 2.3 volts, 60 milliamps. We're only 0.3 volts above its rating and we're drawing 60 milliamps. Now that's more than I feel comfortable running this LED at, so let's take it back down. So when you apply voltage to an LED, you do not want to exceed its rating. Otherwise, you'll be drawing excessive current, and if that current is too high for the LED to handle, the LED will blow up, and it will smell really bad, so don't do that. Now let's see what happens when we hook up a series resistor with it. There we go, we have a series resistor with it now. So right now we have 2 volts, and the LED is on. It's dimmer than before because we have some current limiting, but it's still on, so let's crank it up now. There we go, 2.2 volts, and we're still under 10 milliamps. 2.7, we're still good. 3 volts, we're still fine. 4 volts, we're still fine. And here you go, 5 volts, we're around 10 milliamps. Now, how is this happening? Why aren't we drawing 1 or 2 amps out of this? Well, that's because the LED is still only dropping 2 volts, and I'll show you that with my multimeter in a second. The reason being is because this resistor is dropping all the rest. The LEDs will always want to drop whatever their rating is, and then whatever else is hooked up will drop the rest. And in this case, the resistor is hooked up to it, so the resistor will drop the rest. And here, I'll show you that real quick on my multimeter. Give me a second here. As you can see, besides that first turn where I actually had in the current, don't do that. Make sure when you're measuring voltage, it's in the voltage plug. That was very bad of me. But as you saw measuring the voltage with my multimeter, that LED is running at 2 volts, even though this applies at 5 volts. That's because the resistor is dropping at 3 volts. And the resistor will drop all the excess voltage, whatever the difference may be between the 2 volts of the rating of the LED and the voltage supply. So let's measure the resistor. As you can see, the resistor is dropping 3 volts. So 2 on the LED plus 3 on the resistor is 5 volt supply. So if we take it up to 9 volts, let's go down a half. Now what do you think the voltage on the LED will be? Let's measure it. As you can see, although it's a little bit higher, it's around 2.116, it's still right around its rating of 2 volts. So the reason it's higher is because you're drawing more current. So that's something to be aware of. So how much do you think the resistor will be dropping if the voltage supply is 9.5 volts, and the LED is dropping 2.16. Let's measure it. As you can see, is with this type of setup, the rating of the LED will always be what's on it, regardless of what the power supply voltage is, because the series resistor will drop all the rest of the voltage. I should turn that down. We're drawing a little bit too much current. So as you can see, when you get a voltage reading on your LEDs, those are the voltage ratings that the LED will run at, and that's actually an important figure when calculating resistors. The way you calculate a series of resistors is you take your voltage supply voltage, which in this case, let's fix it, make it be 5 volts. You subtract the LED's voltage, in this case 2 volts for the red one. You take that remainder, which is 3 volts, divide that by the amount of current you want to run through it, in which case, let's say 10 milliamps, and that'll give you the resistor you'd want to use to properly control the current of the LED. So in this case, we have 5 volts minus 2 volts, which is 3 volts at 10 milliamps. That's around 300 ohms. There's actually a 220 ohm resistor, and the reason is because this isn't very accurate. This is only accurate to every 10 milliamps. So if this was 12 volts, let's say, as you can see, we're drawing 40 milliamps, and that's rather excessive. So if we have 12 volts on the supply, we have a 2 volt LED. That means the remainder is 10 volts, and we want to draw 10 milliamps. So 10 volts divided by 10 milliamps means we'd want to use a 1K resistor to be drawing 10 milliamps right now instead of 40. So even though you could use the same resistor for different voltages, you always want to calculate a proper series resistor in order to keep your current to be an appropriate value. And 10 milliamps may be excessive and may be too bright, so if that's the case, use a higher value resistor. But you typically don't want to draw more than 10 milliamps if you want it to last a long time and not have problems with it, especially if you're powering it from a microprocessor pin. If I was actually powering this from something like this Arduino, then you definitely don't want to draw more than 10 milliamps per pin. You might be able to draw more, but I wouldn't push your luck, if you will. Now I also have another LED here, which is a blue one, and according to the sheet, the blue one is 3 volts to 3.2 volts. So let's play with that one a little bit. Take the right one out. Now this one is hooked up directly again. Let's see what this one will do. 2 volts, nothing. 2.5, there we go. It's rated for 3 to 3.2, and like I said, it will turn on earlier, but that rating is where it draws 10 milliamps. So let's see if that's right. 2.6, 2.9, there we go. 3 volts, we're drawing 10 milliamps. So that's what those ratings mean. And those ratings mean where it will draw 10 milliamps. So you can see the LED is on. No problem at 3 volts. Let's crank it up a little bit more. So we're on a 3.2 volts, we're drawing 20 milliamps. Let's go up to 3.3 volts. At 3.3 volts, we're running a 3 volt LED. As you can see, you can do this just fine, but look at the current, we're drawing 30 milliamps. That may be excessive for a lot of applications. I wouldn't want to hook this up to an output pin of a microprocessor that runs 3.3 volts. That's just too excessive. So even though you could run an LED with no resistors, you'd typically always want to run a series resistor with it just to prevent too much current. As you can see, let's hook up the series resistor back up to it. And just like the red one, let's take up the 5 volts. Now this one is a little bit different than the red one. We're not drawing 10 milliamps anymore. We actually have to crank it up a little bit more, right around 5.6 volts to get 10 milliamps out of it. The reason that is because this LED has a higher voltage drop. It has a 3 volt instead of a 2 volt voltage drop. Whereas before we had 5 volts minus 2 volts, which meant the resistor dropped 3 volts. Right now the resistor is only dropping 2 volts. We have 5 volt supply minus 3 volt drop of the LED, which means there's only 2 volts left. So that means this resistor is dropping 2 volts. 2 volts, and this is 220 ohms. that means we're only running around 9 milliamps of current through this. And as you can see, that'd be the fourth digit here, which this thing can't display. So that's just something to be aware of with those ratings, is that they're important to a degree, but usually when you have a series resistor like this, it's not that critical. Let's take it up to, say, 9 volts, and let's measure what the multimeter tells us the LED actually is. As you just saw, the multimeter said it was 3.2 volts, and that's exactly what our little spec sheet said. So with the series resistor, even though the voltage supply is at 9 volts, the LED is still only dropping 3.2 volts. All the rest of the voltage is being dropped through that resistor. So we could crank that voltage higher and lower, and if it's higher, the resistor will drop that voltage, and if it's lower, well, the LED simply won't turn on because it's not enough to make it conduct. So let's go to, there we go, 2.3 volts. The LED is not on because there is not enough voltage to actually turn it on. Now, one circuit that I have here, which is very simple, is a single transistor, a base resistor, and then the LED. Let me hook that up accordingly. Now what this circuit does, very simply, is it's a constant current source. So regardless of what you have hooked up to it, either a 1 volt LED, a 2 volt LED, 3 volt, or even a 5 volt LED, what it's going to do, it's always going to supply the same amount of current through it, regardless of what the voltage is. So let me demonstrate that real quick. And the reason I have an Arduino here is to give me a constant 5 volts, which is what I'm running the base off of. So I'm actually not using any of the pins, I'm just using this for a USB breakout for 5 volts. So let me show you real quick what the circuit does. So we're at around 3.1 volts, 3.5 volts, and we're drawing right around 10 milliamps. Now look very carefully at the voltage, the current, and the brightness of the LED. 5 volts, still 10 milliamps. 9 volts, still 10 milliamps. 12 volts, still 10 milliamps. Keep going up. Let's go up all the way. 21 volts. We're up to around 20 milliamps now, and I'll explain why that is here in a second. But note the brightness as I turn the voltage down. Do you see getting any dimmer? I don't. There you go, now it gets a little bit dimmer. So around 3 volts it gets to its maximum brightness, and then it stays at brightness. And the reason it does that because the way the circuit is set up is, as I mentioned earlier, is a constant current source. So we're always trying to run around 10 milliamps through the output. So even if there's a blue LED or the red one, it'll always be around 10 milliamps, which is what we calculated. Let me explain the circuit real quick. We're using a feature of the transistor called DC current gain, which is notated as HFE. That's the amount of amplification that happens with the current. So the way this transistor is set up is the emitter goes directly to ground. The collector goes to the cathode of the LED, which is the short leg. The other end of the LED goes to the voltage supply, whatever it happens to be, 3.3 volts, 5 volts, 9 volts, 12 volts, 20 volts, it doesn't matter. And then the base goes to a base resistor. And this is the key component where you have to calculate carefully in order to control that LED. There's no series resistor on the output of this transistor with the LED. It's just supply, transistor, LED, supply. The other end of the base resistor goes to your microprocessor. Now, this signal line you could hook up to anything, and it takes no current to turn on. As you can see, just me touching it supplies enough voltage and current to actually turn it on. So when it's grounded off, it's off. When you hook it up to the supply, it's on. And you could easily hook up 3.3 volts or even 1 volt up to this. As you can see, just touching will turn it on. You just have to calculate the appropriate base resistor. So let me put this back on, the constant 5 volts. There we go. And let me show you real quick how this circuit was actually calculated and where you can find this information. The transistor I'm using right here is a 2M3904. So in order to find the information, all you have to do is, let me adjust my camera here, is go to Google and type in data and the part number you're looking for. In this case, 3904. Hit search, and then it's typically the first link. It's usually a PDF. And then there's the data sheet for that device. It comes in several different packages, and you do want to note the basing of the package. So in this case, it's EBC, looking at it from this orientation. Now, if you know how to read data sheets, you can make sense of all these numbers, but those aren't really important for our application currently. What is important is this figure right here, the DC current gain, notated as HFE. Now, what we're doing right now is we're running 10 milliamps through that collector, and that's what IC denotes here. IC equals 10 milliamps. That's what we're running in our circuit. And they say for this application, the current gain is between 100 and 300. This VCE is just the voltage they use to get these numbers, but that's not really important for our application. So we use these numbers, let's say 100, to calculate that base resistor. So if we want 10 milliamps on the collector and the beta is 100, that means we want 10 divided by 100 on the base, which is 0.1 milliamps. So we want 0.1 milliamps on the base. In order to do that, we take our base voltage, which in this case is 5 volts coming from the Arduino. 5 volts minus 0.6, and the reason I say 0.6 is because between the base and the emitter there's a 0.6 voltage drop, and you do want to take that into account to get more accurate figures. So 5 minus 0.6, which is 4.4, divided by 0.1 milliamps, which is what we calculated needs to be the input current to this transistor. So if we do that, 4.4 divided by 0.1, that's 0.1 milliamps, that is, don't forget the other zeros, that's 44K. So this resistor right here is actually a 44K resistor running into the base, inputting 0.1 milliamps into the base. That means on the output we should get around 10 milliamps out. Now, as I was saying earlier, if I crank this up to 21 volts, the reason you see 20 milliamps is because it's actually running between 15 and 20 milliamps through there. The gain is a little bit higher than 100. There's a few reasons for that, just manufacturing differences, and also there's a Westinghouse transistor as compared to the data sheet was for a Fairchild. So it's a little bit off, but it's usually close enough where it'll make the circuit work. As you can see, I mean, it's no problem even if it's this far off, it's fine. So let's put it to a more reasonable voltage, say 5 volts, and we go actually measure the current running through the circuit. So switch your meter to current, move the lead over. Alright, that's it. Now, as you might have seen, is that the current pretty much runs between 17 and 20 milliamps. The reason it also fluctuates to that degree is as the voltage goes up, the beta does also change a little bit. Looking at the data sheet, if you will, real quick. It doesn't really say it here, but on these tests, it says they were done at 1 volts, and as the voltage changes across the collector and the emitter, the beta will change a little bit, which is why you were seeing a difference between 17 milliamps and 20 milliamps. But again, that's so minor, I don't think it's going to affect anybody's circuit really. So as you can see, the beta is a little bit higher than 100 that I calculated, but even so, that's still fine. So right now, regardless of what the power supply voltage is, we'll always be getting around 15 to 20 milliamps in the output. So we probably want to use a little bit bigger resistor to give us a little bit less current on there. Let me hook it up back real quick. So as you can see, this is just one very simple circuit in order to control an LED. Very simple, just one transistor and one properly calculated resistor. And then regardless if you hook up a 1 volt, 2 volt, 3 volt, 4 volt LED on there, it'll always be the same amount of current. It'll be 10 milliamps, whatever type of LED you hook up to it. Granted that the power supply is high enough to actually power it. So this is just one simple way to control, and then the microprocessor pin requires no current, so you could hook up a million of these to a microprocessor and you wouldn't kill it, because you can see just touching it supplies enough voltage and current to turn it on. And that's one easy way just to make a circuit where it doesn't matter what your supply voltage is, as long as you do the calculations properly, the LEDs will always work and you won't have problems with it. Alright, thank you for watching.